Okay, so these are the notes for 6.3 Intro to Vectors. And so let's just get started with example 1. Please do make sure that you read the information up above. It's got some important definitions that you are going to be required to understand. Okay, so let's start with number 1. Let vector u be from the point P of 0, 0 to Q, 5, 8, and vector v be from R, which is at 3, 11, to S, which is 8, 19. Show that vector u is equal to vector v. In order to show that vectors are the same, we have to show that their magnitudes are equal. We have to so that the magnitude of u, and vectors always seem to look like they're really bolded. The magnitude of u has to be the same as the magnitude of v, and that they have to be going in the same direction. So we need to show that the slope of u equals the slope of v. Okay? Those are the two things we need to do. So it's really important that you understand and you pay attention to where your vectors are. Ours is starting at P and going to Q. So to find the magnitude of u, it's kind of like doing Pythagorean theorem. We're going to do the square root of where it starts taken away from where it ends up. So it ends up at Q. So I'm going to go 5 minus 0 squared plus 8 minus 0 squared. Simplify that, and that gives me the square root of 89. Okay. Now if I look at the slope, it's kind of like, if you remember, slope was y1 minus y2, so forth. Well, we want to go from where it ends up. It's ending up at Q, so we're going to subtract the y values of Q from the y value of P over the x value of Q minus the x value of P. And I get 8/5. And again, this was the slope of U. Now let's do V. We're going to do the exact same thing. We're going to take the square root of the difference of our points. So the x component of the s is 8. I'm going to subtract that from the x of my r, which is 3. And again, the reason I'm doing s first is because that's where it ends up. You want to go from the end minus the beginning. Plus, now do the y values, 19 minus 11. These numbers are a little bit bigger, so I'm going to actually use another line. So it gives me 5 squared plus 8 squared, and that's also the square root of 89, which is, so far it matches the other one. That's what I want it to do. Now for the slope of V, I'm going to take the 19 minus the 11 over 8 minus 3. 19 minus 11 is 8. 8 minus 3 is 5. So because the magnitude of u equals the magnitude of v, and u and v are going in the same direction, so vector u and vector v, that was supposed to be an and sign, are going the same direction. We can say that vector u is equivalent to vector v. So again, in order to show that two vectors are the same, you have to show that they have the same magnitude and that they're going in the same direction. Alright, so let's go down to the next one. It says given that vector v is 6, -5. Now this is component form here. So it tells me I'm going 6 in the horizontal, -5 in the vertical. And in standard position. That standard position is very important. That means my initial point of my vector is going to start at 0, 0. So that means that since my horizontal component is 6, that means I am moving 6 in the horizontal direction and 5 down. Okay. So there's my vector. Okay. So now I want to find the magnitude and the direction. So I can now use my Pythagorean theorem to find my magnitude. And I can just look at my picture, which is my triangle, and say it's 6 squared plus 5 squared, and that's just the square root of 61. Okay, there's my magnitude. Now the direction is going to again be the slope. And that would be then, it's going down, it's -5 over 6. Alright, that's example 2. Let's keep moving. Alright, so number 3, given vector v is equal to -8, 3, and it's in standard position. Again, standard position means its initial point starts at 0, 0. Find the magnitude of v, and then find a unit vector u with the same direction as v. So let's find our magnitude first. And again, we're just going to use Pythagorean theorem. We're going to take our horizontal component squared plus our vertical component squared. And that's going to give me the square root of 73. To find our unit vector v, or unit vector u, the way to find a unit vector is one that has a magnitude of 1. Let me rephrase that. A unit vector has a magnitude of 1. So in order to find it, I'm going to take my components of my original vector divided by its magnitude. So the components of v are -8, 3. Be very careful. You try to make sure you're using the little arrows, kind of less than, greater than signs. Don't use parentheses. That's going to be divided by the square root of 73. Not 37, 73. Okay? All we have to do now is we can actually apply that square root to both of the components, and we end up with -8 over the square root of 73, comma 3 over the square root of 73. Rationalize your denominator, and our unit vector is -8 square root of 73 over 73, comma 3 square root of 73 over 73. Okay? And there's our vector u. That is a unit vector that is going in the same direction as v. Okay? Let's move on to number 4. Now number 4 has different parts, so I'm going to just do each of the different parts separately. So part A says, I want to find negative vector u, meaning I want to go in the opposite direction of it that it's going now. So all I have to do with that is I have to do the negative of my components. So all our rules still apply. We're going to do distributive property. So that makes it negative 3, positive 5. And that's all we have to do, because now instead of our original vector was going to the right 3, down 5, now it's going to the left 3, up 5. So it's going in the exact opposite direction. Part B has negative 2u plus, or excuse me, minus 7v. Well, I know u is 3, negative 5. So that's going to be negative 2 times the component of 3, comma, negative 5 minus 7 times the components of v, which is negative 8, comma, 2. So distribute, and I get negative 6, comma, 10. Negative 7 times negative 8 is positive 56. Negative 7 times 2 is negative 14. Now here's the cool thing. We can actually add the same components together. So my horizontal components, the negative 6 and the 56, I can just add them together. And I get 50. 10, negative 14 is negative 4. So what that all comes down to be is that my resulting vector is going 50 to the right and down 4. All right, let's go on to C. And I want 3 vector u plus 4 v. So now what I want to do is I want to distribute that 3, and I get 3 times vector u plus 12 times vector v. Apply my components. The components for u are 3, negative 5 plus 12 times u, or vector v, is negative 8, comma, 2. Alright, so here's what I'd like you to do is pause your video and finish this one off. Do your distributive and combine like terms and see what you end up with. And you should have ended up with a negative 87, comma, 9. So it's going 87 units to the left and up 9. Alright, so that's example 4. Let's move on to example 5. Okay, so for example 5, it says let vector u be the vector from negative 5, 9 to 4, negative 1. Write u in component form. So I'm actually going to graph it for you this time. So if I plot my points, I'm going to plot negative 5 and 9. So I'm going to count over to negative 5. Okay, remember, use 2 fingers to... So that's way up here, and I just barely fit it on there. Okay. So this is my initial point. terminal point is at 4, negative 1. So I'm going to go over to 4, negative 1. So I'm going to draw my vector connecting these two. Okay. Now to find it in component form, I am going to basically make like a right triangle. Okay, so I'm going to connect them. So I'm going to get my horizontal component going right here, and my vertical down here. And I could count the boxes if I wanted, and I get 1, 2, 3, 4, 5, 6, 7, 8, 9. And then counting down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so I could write this in component form is I'm going horizontally to the right, so that's positive, and 10 down, so that would be a negative. Okay? But what if I didn't want to have to draw a graph? Here's what I would do. I can do it algebraically. I could subtract my terminal point from my initial point, so I could take the components of 4 minus negative 5, comma, again, subtract the y, same way, just take your terminal point minus the initial, and I get the same thing. So either way will work. The biggest thing I want you to pay attention to is these things right here. Make sure you don't make them parentheses. They have to be, kind of looks like, greater than and less than signs. You have to do that. If you do parentheses, you have a point. You don't have a vector. So make sure you draw it correctly. Don't get lazy. Don't do it too fast. Make sure you put that point in there. All right? That's number 5. Let's move on to number 6. Okay, so 6 says, given vector v is equal to 8, it has the components of 8, negative 6, and it's in standard position. Find the unit vector u in the same position as v. So we've already done a problem very similar to this. So if you remember, to find a unit vector, it's going to be the original vector that we want, which is going to be vector v divided by its magnitude. So the first thing we need to find is we have to find the magnitude of v. So let's do that down here. And it's the square root of the sum of the squares of the components. So 8 squared plus negative 6 squared. And that's the square root of 64 plus 36, which is the square root of 100, and so our answer is 10. So there's our magnitude. So now going back up here, my components of v are 8, negative 6, and we're going to divide that by the 10, which was my magnitude. Now distribute. The 10 to both parts of the components, and I get 8 over 10, comma, negative 6 over 10. Reduce. And I get 4 over 5, comma, negative 3 over 5. Now this time, though, I'm going to show you why this is called a unit vector. A unit vector, again, is a vector that has a magnitude of 1. So if I find the magnitude of u, it should come out as to be a 1. So let's just do that. So the magnitude of u would be the square root of the 4/5 squared plus the negative 3/5 squared. Well, 4/5 squared is 16 over 25. Plus the negative 3/5 squared becomes 9 over 25. If I add those together, I get the square root of 25 over 25, which is 1. So my unit vector does have a magnitude of 1. Alright, so that is example 6. Let's move on to example 7. Okay, so we're on number 7. It says let vector u equal negative 4i plus 7j and vector v equal 9i minus j. Now you're probably wondering what these i's and j's are. This is called the linear combination for a vector. It's another way to write it, but we still do everything the same. The I is the horizontal component, the j is the vertical component. So what we're going to do is we're first going to do 1/3 of u and that's going to be negative 4i plus 7j minus 5 times vector v, 9i minus j. Distribute negative 4/3 I plus 7/3 j do the negative 5 over. Negative 5 times 9 is negative 45i. Negative 5 times negative j is going to be positive 5j. Combine like terms. We can get a common denominator if we want. And that would change the 45 times 3 would be, so that'd be negative 4/3 I plus 7/3 j minus 135i plus, and let's might as well just change this 5 to have a common denominator too, 15j. So negative 4 plus negative or minus 135 is negative 137i over 3. Negative or 7 plus 15 is 22j over 3. Alright, so there's our result, our final vector in linear combination form. Alright, let's move on to number 8. Okay, let's move on to example 8. Example 8 says find the direction angle of vector u that has components of 7 and 11. So what we're going to basically be doing is I want to plot this. So if it's in component form, that means that the vector is in standard position, so it starts at 0, 0. And since my horizontal component is positive and my vertical component is also positive, it means I'm going to go to the right 7 and up 11. So I'm just going to kind of sketch it in here. I am going to make a triangle with it, listing my horizontal at 7 and my vertical at 11. And it's just a sketch. And what my directional angle is what is my theta right there going off of the x-axis? So what I'm going to do is I'm going to use tangent. Tangent of theta equals 11 over 7. So theta equals arctan, or tan to the minus 1 of 11 over 7. And it tells me that theta is 57.5288 degrees. And I know that that's my angle because I am in the first quadrant, so I don't have to adjust it at all. And that's my directional angle. Alright, let's move on to number 9. I want to find the directional angle for this vector. So again, I'm going to put a graph on there, so why don't you sketch the graph. This time my horizontal component is -8 and my vertical component is -16. So that means I'm going to be going to the left and down. Alright. Same thing, I'm going to draw a triangle. This is my 8, and here's my 16. And again, my directional will be going from here to here. Now the problem is if I do my tangent, my inverse tangent, I'm going to get an angle that's not in this quadrant. So let me show you that. Because this isn't on our unit circle, so we're going to have to use our calculator. So if I did tan of theta, that would be -16 over -8. And if I type that in my calculator, using my arctan, or tan to the -1, -16 over -8 becomes +2. I get that theta is 63 degrees, 63.4349. But looking at my picture, I know that my angle's not 63 degrees. It's bigger than that. Remembering our restrictions for tangent, our calculator is only going to give us angles that are in the first quadrant or fourth quadrant, because that's the restriction for arctan. We can adjust it to where the actual angle is, in this case by adding 180 degrees, so I move it from the first quadrant down to the third quadrant. So I'm going to add 180 degrees. And I get 243 degrees, 243.4349 degrees. And there's my directional angle. Okay, so that's the notes for our first section on